All right, so we're kind of getting ourselves accustomed to the idea of thinking of a sample as being a statistical unit. It's intermediate between the individual and the whole population. There are basically three levels of sets here. The individual is one item in the population. A sample is several of those items. So each one of those can really be thought of as a unit. Thinking of a sample as a unit is kind of a new idea that we're experiencing today. So we're walking ourselves through it part by slow part. In the last video clip, we introduced ourselves to the concept of a sample's error, which is, again, the difference between that sample statistic and its population's corresponding parameter. Now we're ready to develop another really big concept, which is the idea of a sampling distribution. A sampling distribution is a new distribution whose members are samples from what I will now call the parent population. That's quite a big bite to chew on. So we're going to walk ourselves through this for a few minutes. Let me just read that one more time. We're going to be taking a parent population. We are going to be drawing samples from that parent population, and then we're going to be throwing those samples onto a pile. And the way those samples stack up will be an absolutely new distribution, and it's going to be called the sampling distribution. Now that name kind of makes more sense, doesn't it? All right, big concept. So let's look at some visuals here. Okay, so let's start out with the sampling distribution of proportions, because we've actually foreshadowed this already. We've actually seen this. If you remember the visual that I gave you of the Galton board, the pegs on the board and the ping pong balls bouncing down that board, which can bounce either right or left, success or failure. There's only two options, and that's the same with a proportion problem. Every proportion problem also involves only two options, either success or failure. So let's take a look at a binary or binomial population. Binary, again, means that every item in the population is either a success or a failure. And in the example that I'm presenting on the screen, this population has a proportion of successes of 60% or 0.6. So we kind of have to zoom in on the labels to read them more easily. But this bar represents successes, and this one represents failures. So we always kind of think about these bars as being filled with sand, right? Every grain of sand in this case is one individual member of the population. And there are more successes than failures, and that's why this bar stacks up higher. An alternative visualization is the pie chart. These really represent the same thing. So you can represent this all together in one pie. 60% of the items are successes, and another 40% are failures. By the way, we use the letter lowercase q to represent the proportion of failures. So in this case, if our population is 60% successes, then all you have to do is subtract from 100%. It would be 40% failures. So in this example, Q would be 0.4. I kind of like the pie chart visual, because now what I can imagine doing is throwing darts at this dartboard. So let's take a sample of size 100. If you threw 100 darts at this dartboard, how many of those darts would you expect to hit the success zone? You'd probably expect about 60 of them, right? Will it always be exactly 60? No, because of sampling error. Remember, some samples, in fact, most samples are a little bit different from the population. So we'd probably expect that most of the time, about 60 darts would hit the success rate. All right, so what we're going to do is we're going to draw a sample of 100 from this population. So let's basically kind of model it by throwing darts at the dartboard. I throw 100 darts at this dartboard. 57 of them are successes. Okay, so now I have one sample proportion. I take that one sample proportion, a new grain of sand, and I put it on this pile. So what we're going to be piling up over here is an absolutely new distribution. It is not the population. It's a new distribution. Each grain of sand in this pile represents not one individual, but one sample. And we've got to keep that sample size fixed. So I'm illustrating with samples of size 100. Lowercase n equals 100. All right, so there was a 57. Just imagine one little grain of sand there at 57. All right, now it's your turn. You throw 100 darts at the dartboard. Okay, good job. Good throwing. You found that 64 of them ended up as successes. Okay, so your grain of sand is 64. Let's put that one on this pile. Okay, now it's her turn. Now it's his turn. We take millions and millions and millions of turns. Every single student who throws darts at this dartboard writes down their number, puts it on a grain of sand, throws that grain of sand in the pile, and eventually those grains of sand begin to pile up into a meaningful shape. So we need to understand how to characterize this shape. Essentially, when we characterize or parameterize a distribution, we need to know three things about it. We need to know a measure of center, we need to know a measure of spread, and we need to know its shape. Center, spread, shape. So the question is, if we piled up all these grains of sand, where would they be centered? How wide would the curve be, and what would it be shaped like? And I've kind of represented those questions here. So understand that what we're piling up on this pile is samples, and each sample has a proportion which we call, remember, p hat. So this is the p hat axis. The number right in the middle, the mean. Sorry, I got a little bit distracted there. Somebody knocked on my door. All right, so the point is that the numbers that we're piling up here are sample proportions, but we need to think about those as being units. So if you have a pile of units, that pile is going to have some average. So that's labeled here as the mean of the sample proportions. Okay, it's one statistical concept inside of another, so that makes it a little bit tricky, but we are piling up sample proportions, and those sample proportions must have some mean. So we call it the mean of the sample proportions, and therefore it's abbreviated as mu with the subscript of p hat. Furthermore, this pile must have some width. It must have a standard deviation, the half width of the heart of the distribution. So these sample proportions have some standard deviation, and therefore we call it the standard. I'm sorry, I used the word deviation. I should have used the word error. Why? Because these are not individuals anymore. They're samples. So remember that samples have errors. The distance between, or the difference between the middle and a particular sample is in error. So the widths on this curve are called standard errors, but they really represent the standard deviation of the sample proportions. All right, so how do we calculate these numbers? It turns out there's formulas for it. And the middle one, the one in the middle, is very intuitive. So if I ask this question to pretty much anybody, they'd always get it right. After 1 million people throw darts at this dartboard and throw all their scores on the pile, what number do you think would be in the middle of that pile? Where are most of our samples clustering? And I think most students would say, well, probably usually around 60%. Yep, that's right. Okay, so we just borrow that from the population. The mean of the sample proportions is equal to the population proportion. So 0.6 goes right in the middle. Oh, good. That was an easy concept, very intuitive. The next one is not intuitive at all, but fortunately it has a very simple formula. The standard error of sample proportions, aka the standard deviation of these proportions, turns out to be the square root of PQ over N. So now I hope I'm impressing on you how important it is to understand which numbers represent which letters. because these formulas give you letters. You're going to have to plug numbers in for those letters in your formulas. So in our example, this would be calculated as, let's see, what did we say P, Q, and N were again? Yeah, so in our example, P was 0.6, therefore Q is 0.4. The sample size is 100, and you can just calculate this on an ordinary handheld calculator. And the first few digits you'll find are 0.0489 if you do that correctly. Finally, what is the shape of this curve? The answer is it'll be a normal distribution. Surprise, surprise. As long as the following conditions are met. N times P must be at least 5. What NP represents, by the way, is your expected number of successes. So in our example, we threw 100 darts. Each one had a 60% probability of success. 60% of 100 is 60. Okay, so that's basically how many. It really represents how many successes you expect. So both the number of successes and the number of failures that you would expect to get should be at least 5. And in our problem, that would be 60 and 40, well above 5. So that rule would follow, and we'd be able to conclude that our pile would be normal, or at least close enough to normal to use normal formulas.